Assalamualaikum, good morning. Okay, I know that everyone is still moody, cannot move on, some of us. But anyway, we should finish up our syllabus. It's the second last topic. Second last lah. Chapter 6. Quantum dot solar cell. This is a very different than the other solar cell. These are the learning outcomes for the quantum dot solar cell or QDSC. Two outcomes only. One, to understand the advantages of QDSC compared to the silicon-based solar cell. So it has certain advantages, and we will discuss about that. Understand the factors that preventing from achieving high efficiency quantum dot solar cells. So if you refer to the statement number 1, it shows that the quantum dot solar cells maybe has something extra if we compare to that of the silicon solar cell. But if it has so many advantages, why does the quantum dot solar cell has not been used in the industry or it is being commercialized? Because it has some preventing factors that we also will discuss about that. Now again, let us take a look at the state of the art of solar cells. This is very important. We have the first generation, we have discussed about that. Mostly they are crystalline solar cell, including the crystalline, monocrystalline silicon solar cell, monocrystalline. And we have the second generation solar cell, which is the thin film solar cell. We use small amount of material, for example, the hydrogenated amorphous silicon, or even the polycrystalline silicon. So then we have the third generation solar cell, which is known as molecular absorber solar cell, still in the research domain. Both of the first and second generation, they already established in the commercial domain. But this one, the third generation, still in R&D due to some hindering factors, which we will discuss about that. And if you look at the theoretical photovoltaic conversion efficiency, the first and second generation solar cells, they are limited to 32% because of this. When the solar cell absorb one photon, they only could produce one exciton. One photon is absorbed, only one exciton is produced. What is exciton? Can you still remember what is exciton? It's a pair of excited state electron and the hole in the valence band. So one photon absorbed, only one exciton is produced. Unlike the quantum dots. Quantum dots is different. Upon absorption of one photon, they could produce more than two excitons. The rest of the solar cell, absorption one photon, one exciton is produced. But quantum dot solar cell, absorption of one photon, they could produce more than two excitons. And this has increased the theoretical efficiency of quantum dot solar cell to 62%. One exciton is produced, it is limited to 32%, the theoretical efficiency. If they could produce two excitons, they could reach 60%, at least. If they produce two excitons, how about if they produce three? We could achieve near 100% of conversion efficiency. So we are aiming for that. So we have die also is the same, limited to 32%, cannot produce more than one exciton. However, okay, let us see. If we look at the experimental, the real photovoltaic conversion efficiency, all of the first and second generation solar cell, they are reaching to the limit, 29, 28, 21. But the third generation solar cell, this one, for example, the solar cell, the limiting efficiency is 32%, but it only reached 32%. Quantum dot solar cell, even though it promising more than 60% of efficiency, they only could show 8.6% so far. This is the real photovoltaic efficiency. And because of this, we cannot commercialize the quantum dot solar cell. We need to find a way to overcome few hindering factors. For example, the usage of ligand, so on and so forth. We will discuss about that. Only 8.6, so we discuss about this. Why it is still below 10%. So this is the problem in quantum dot solar cell. Although theoretical efficiency of quantum dot solar cell is exceeding 60%, Unlike the crystalline silicon, they promise 32%, but they are reaching 29%. Quantum dot solar cell, it promises more than 60%. However, it only reached 8.6%. So this is the problem. Even though it is promising exceeding 60%, a device demonstrating a considerable fraction of it is not so far realized, only 8.6%. This is the problem in quantum dot solar cell. Theory promise very high efficiency, practical below than 10%. What is the problem in quantum dot solar cell? Before that, we need to take a look at the main mechanism that produces more than one exciton. It is called as multiple exciton generation, or MEG. Multiple exciton generation, or MEG. So we have, for example, on your left hand side over here is the energy level of the bulk semiconductor. Let's say we have a bulk semiconductor. This is the conduction band. The yellow is the conduction band, and the blue one is the valence band. Okay. Upon absorption one photon, Again, upon absorption of one photon, this electron will be excited to the conduction band. And if we did not match this bulk semiconductor with the other component and no p-n junction is produced, this electron finally will recombine with the hole again. Not recombine. It relaxes to the lowest valence band. To the lowest conduction band, and the energy is wasted as heat. Again, let me show you again. This electron absorbs one photon from the sunlight. This electron will be excited to the conduction band. It may exceed the band gap. It may be excited more than the band gap because it could absorb energy more than the band gap value. And then this electron will relaxes to the lowest valence band, conduction band. It relaxes to the lowest conduction band. Ini bukan recombination, this is not a recombination, but it's a relaxation. The name of this mechanism is relaxation. And during the relaxation, energy is wasted as heat. And we only could get one exciton. One photon is absorbed, one exciton is produced. Unlike our friend over here, the quantum dot, upon absorption of one photon, this electron could be excited more than the value of the band gap if it absorbs the high energy photon. Now this electron will finally relaxes as well. It will relax to the first or second, to the second or the first LUMO. And during this relaxation, what will happen is that photon is produced. Energy is not wasted. This one energy is wasted as heat, but this one energy is wasted as photon. Heat, photon. And if the energy of the photon produced is greater than the band gap, it means that this photon could be reabsorbed by the neighboring electron. This photon will be reabsorbed by the neighboring electron, and this electron will be excited up to this level. Now, how many excitons do we produce? Two. So, why does this one is producing heat and that one is producing photon? Can anyone answer that? Why the quantum dot is producing photon? Why is the bulk semiconductor is producing heat? Any idea?
Infrared spectrum.
Which one? That one. Okay, infrared spectra. Lagi?
Visible light.
Which one? Visible light. This one. Okay, lagi? Band gap. Elaborate. The band gap of QD, More? So again, the question is that why does the bulk semiconductor during the relaxation of excited state electron in the bulk semiconductor doesn't produce any visible light. Instead, it is producing infrared light. So this is what happened. The first thing that you need to show is the energy levels. We have the conduction band. This is the conduction band of bulk semiconductor. Remember, bulk. Tak nampak. And we have the valence band of bulk semiconductor. So in this band, they have so many energy levels, which is closely separated to each other, very close. Okay. Then we have quantum dots semiconductor. Maybe like this. This is QD. Yep. Kena ikut skala ni, salah. Tinggal lagi ni. Bolehlah. Let's see. Can you see the difference? The energy levels, they are closely separated to each other. But this one, they are widely separated. They are largely separated. This is LUMO 0, LUMO 1, LUMO 2, LUMO 0, LUMO -1, LUMO -2. This is the first stage. So let's see if we excite an electron over here. So if we have electron over here and the electron is being excited, is absorbing the photon from the sunlight. If the photon is greater than the band gap, this is the band gap. Okay. If the photon is greater than the band gap, what will happen that this electron will be excited? Maybe up to here. This is whole. This electron need to relaxes to the lowest conduction band. This is lowest conduction band. So what will happen is that it doesn't fall directly. Instead, it will fall to the first energy level, then second energy level, to the neighboring energy level, neighboring energy level, energy level, energy level, energy level. And each of these relaxation to the each energy level, it will emit wave. And this wave length, the energy is very, very low. See, the energy gap between the energy level is very small, right? It means very small energy will be lost. And that small energy is correspond to the wavelength of infrared. Unlike this one, when the electron is being excited, if it is absorbing, for example, up to this point, if the electron is absorbing energy greater than the band gap, it will be excited. Maybe up to this point. And this electron also will relaxes, but it doesn't relax to any. Do we have any energy state in between LUMO 1 and LUMO 0? No. It will relaxes over here. This very large gap. And this gap, the energy between this gap is maybe equals to the band gap. Maybe, could be. And if this electron falls to this energy state, it will also produces photon with high energy, which the wavelength also will be very small, equivalent to visible light. This infrared also will be reabsorbed by the neighboring electron. But can the electron be excited? No, it will move up to this level. It is not excited at all, and it will fall down again. Excited if this electron goes from here to here, but it will goes up with the energy equivalent to the energy which is lost from this recombination, from this relaxation. Understand? This energy level, when the energy is produced, when the infrared is produced, which the energy is equivalent from this difference, this electron will reabsorb the infrared and will try to excite with the same energy which is lost. But it won't be excited up to here, only up to here, equivalent to the energy it is absorbing. Understand? So it is not being excited. Infrared, the energy of infrared light is not high enough to excite the neighboring electron. It is just jump up to this point and goes back again. It's not excitation. It is vibration. This electron absorb infrared and vibrate. Just vibrate. Not excited. Unlike this one, the energy loss is the energy loss from this relaxation is very high, and the energy loss is producing visible light, and this visible light will be reabsorbed by the neighboring electron, and the energy of visible light is high enough to excite this electron up to this level. So 1 photon, 2 excitons. Or if this electron is being excited up to the LUMO 2, it is even better, because we have 2 relaxation. 1 relaxation and 2 relaxation. It produces visible light, and this one also producing visible light. This one producing 1 extra exciton, this one producing 1 extra exciton. So we have 3 extra exciton in total. So if we could get this kind of mechanism, we are reaching 90% of photovoltaic conversion efficiency. 1 photon, 1 exciton is about 32%. 2 exciton is about 64%. 3 exciton is about 96%. We are aiming for that. This is the main mechanism. This is the password to highly efficient solar cell. However, in solar cell, this is not the only mechanism. We have other mechanisms as well. This is the core, just the core. It is already being unlocked, but we need to find the other limiting factor. We will discuss about that after this. So understand? Any question? This is very important. So that is why we are getting extra photon in quantum dot semiconductor. Okay. Let us take a look at the requirement in order for MEG to happen. The first requirement is that the size of semiconductor must be smaller than its exciton Bohr radius. New terminology. Exciton Bohr radius. What is exciton Bohr radius? Okay. After absorbing the sunlight with sufficient energy, this electron will be excited. And the distance, not distance in terms of energy, distance, the real distance when the electron is being excited. What is the distance between this electron and this pole? That is the exciton Bohr radius. Exciton Bohr radius is the distance between the excited state electron and pole. So if the size of our quantum dot, or if the size of our material is smaller than this distance, that material is called quantum dots. For example, if we have material with this size, let's say the material is about 2 nanometer, we use FSAM, we zoom in, we look at with our naked eye, the material is this size. When it absorbs sunlight with sufficient energy, the electron will be excited with this distance. Let's say we have hole here, and electron is being excited from here to there, ataupun up to this point. Electron is excited from this point to this point. So if we compare the distance between the excited state electron over here with the hole over here with the dimension of our material, which one is longer? The excited state electron or the quantum dot or the material? The exciton boron is longer. If this is the case, then our material is called quantum dot. If the exciton boron radius is longer than the material or bigger than the material could be called as quantum dot. Understand? Actually, we have so many terminology for this kind of material, not just quantum dots. If the shape of the material is sheet-like like this, seperti helaian, sheet-like, we could call it as nanosheet. If the material looks like this, we could call it as nanorod. If the material is spherical in shape, we could call it as nanosphere. If the material is superbly small, extremely small, we could call it as quantum dot. So extremely small, we call it quantum dot. This one nanorod, this one nanosheet. And we have so many other types of morphology. For example, nano flower, nano needles. What else? Nano flower, nano needles. Multi-channel nanowire or nanowire, so on and so forth. So, to get an MEG, your material must be smaller than the exciton Bohr radius. And when your material is smaller than the exciton Bohr radius, it means that the energy levels has changed from the bulk, which has closely separated energy levels, and in the quantum dots, it is already changed from closely separated energy levels become widely separated energy levels. I believe I have explained why the energy levels become like that. Okay, one quick question. Let me explain again. Fundamental explanation question. Why does the bulk semiconductor, the energy level is closely separated? And why does the quantum dot semiconductor, the energy levels is widely separated? They are not even band. This one they call as band because they are closely separated. This one is, it is not a band, we call it as molecular orbitals, and they are widely separated. Why it is becoming like that? So you could imagine like this. This is known as quantum confinement effect. Quantum confinement effect. What is quantum confinement effect? So you could imagine like this. I believe I have explained this to you, but I just re-explain to you. Imagine that the whole class is the material. This big hall is our material, and we are the electrons inside the material. So now, can we move freely up and down, front, back and front, left and right? Can we move freely? Can we? Sekarang ni, right now, we can move freely. So this is bulk. So how about if we make this room smaller? Okay, we cut the size of the ceiling, goes down, up to this level. Can we jump up and down? No. So we are confined into dimensional space. We could only move to the front and back, left and right, kan? We cannot move up and down anymore. We are confined into dimensional space. Only X and Y axis, no Z axis at all. So now the movement of electron is being limited to X and Y. How about if we make this room even smaller? We cut down the side of the room. Now the room becomes one narrow hall, one narrow pathway. Can we move left and right? No. Can we move up and down? We only can move forward and back. Now, if we cut down the size of the room again, cut down the size. Up to this point, we cannot move up and down, left and right, back and forth. Can we? No, right? So we are confined in 3-dimensional space. Cannot move. We could only move like this, small vibration only. Same goes to the electrons in the quantum dots. Because of the space is already being too small, so the movement of electron is limited. Unlike the electron in bulk, they could move freely anywhere they want. So because of the movement of the electron is limited, it is changing the band gap and also the space between the energy level. What is the correlation? It is a very long theory to explain. Just memorize that due to the quantum confinement effect, which limited the movement of the electron, the electronic properties of the material also will change. What is the change? The gap between the energy levels is small in bulk. When we reduce the size of the material becomes into the region of quantum dots, the energy level expand. Because of limitation of the movement of electron, the energy level expands. I skipped a very long theory to explain about the electron movement and the expansion of energy levels. I believe it is being taught in solid state code, solid state physics. Anyway, I will make an effort to make another video to explain the correlation between the size of the material, the movement of the electron, and the expansion of the energy levels. I will make that video later and I will publish in YouTube. Okay, understand? This is the reason. Reduction of size, electron movement is limited, so the energy level will expand. Not continuous but discrete. This is called continuous band. This is discrete. We could differentiate between the energy level. Oh, we could see. Actually, this is just imagination, interpretation, artist interpretation. We cannot see the energy level, but we could measure them using the spectroscopy. So this is how it works. So this is the exciton Bohr radius. So can we calculate the exciton Bohr radius for any material? Yes, we have a formula for that. I'm not expecting you to memorize this formula. Any formula will be given in solar cell technology class, examination or test. We don't have test 2, by the way. We only have test 1, which you have took. So the exciton Bohr radius for any materials could be calculated using this formula. And epsilon naught is a constant. Epsilon r is a constant. This one also constant. This is Q, the charge of an electron. This is electron rest mass, constant. This is electron effective mass of electron. This is effective mass of hole. The only thing that is not constant in every material is Me and Mh. Every material they have different Me and Mh depending on the material. So this is an example of calculation of exciton Bohr radius in cadmium selenide semiconductor. The effective mass of electron is depending on material. In different material, the effective mass of electron will be changed. Okay, the answer should be 4.93 nanometer if you calculate it correctly. Now, so we could produce so many type of particle or material which is lower than 4.93. In cadmium selenide, we could synthesize so many sizes of particle which is lower than 4.93. For example, over here, we could synthesize a material with a size of 1.54 nanometer. So, is this quantum dot is good enough? Okay. Okay. Asal dua je. No. This one. Okay, ada. Nanti saya terangkan. We could produce from, let's say for example, 1.5, 2.0, 3.5, something, so on and so forth. until 4.93. They are still called as quantum dot. But which quantum dot is the best quantum dot to be used in quantum dot solar cell? And this is an example to show you that this particle is bigger than the storm radius. And this one we can call as quantum dots. See the size? 6.34. It is way too big. It's bigger than the storm radius of CDSC. So this is not quantum dot. This is quantum dot. And we have so many type of quantum dot which is lower than the storm radius, but we need to select which one of the quantum dot could be used for an efficient QDSC. Now example, the device structure exactly like the dye sensitized solar cell. We just need to replace the dye with the quantum dots. So we have two strategies how to absorb the quantum dot onto the titanium dioxide. First, we could use ligand. Link the ligand with the quantum dot and link the quantum dot ligand conjugate to the TiO2. The second option is that we absorb the quantum dot directly onto the TiO2. We have two strategies. Ligand is linker. Usually we could use mercaptopropionic acid, mercaptoacetic acid, mercaptosuccinic acid. These are known as ligands. We have, let me write it for you. We have mercaptoacetic acid. We could use mercaptosuccinic acid. We could use mercaptopropionic acid. And another one start with B, I can't remember. Mercaptobromic, I'm not sure. Not bromic, mercapto something. Right? So these are types of ligand that we could use to link the quantum dots with the TiO2. But it has drawback. I will explain later what are the drawbacks. Same goes here, dye, this is dye solar cell. The dye will absorb the energy of sunlight and excite its electron. And this is how the excited state electron looks like, the distribution of electron density in the excited state. And we have learned this, the distance between the anchoring hydrogen to the nearest LUMO. The shorter distance, the better the dye will perform. So this is in the SSC. How about in QDSC? In QDSC, no one has ever published the chemical structure of the quantum dots. No one has ever published. So no one has ever studied the correlation between the excited state electron and the efficiency of solar cell. So we are among the pioneer, UMP among the pioneer to study the molecular structure of the quantum dots. We should draw, we should simulate, we should optimize, becomes like the DSSC. So we start that. The working principle similar to that of the dye sensitized solar cell. Similar, just replace the dye with the quantum dots. And don't forget that if we are using the first strategy, which linking the QD with the TiO2 using ligand, the energy level of ligand also should be studied. It has effect because the electron, excited state electron from the quantum dot should be injected to ligand first, then goes to TiO2. We should study this. No one has ever studied before. UMP, the first. And this one, the second strategy, without any ligand, the quantum dot, the electron from the quantum dot could be injected to TiO2 directly. So we should focus on these two strategies. These are the missing links in quantum dots solar cell. We have 6 missing links which most of the researchers did not look at them thoroughly. The first one, chemical structure and emitting states of quantum dots. Emitting states mean that the mapping of LUMO density, the excited state electron location, has not been studied thoroughly. Number 2, absorption cross-section of quantum dot versus dye. I will explain later. This is actually the UVB spectra. Number 3, quantum dot size distribution effect. The sizes, as I mentioned before, we could synthesize so many types of sizes of quantum dot, but which one is the best? We'll explain in the part 3. 4, the ligand effect. Different ligand, they also have different energy levels. they have effect on electron injection. Number 5, redox potential of electrolyte. Just like what you have done in SKLB, we are using salt water and salt solution. In laboratory, we don't use salt solution. We use iodide, triiodide electrolyte. But when we use salt solution, what happens to your cell? It gives voltage, right? It gives voltage and it falls back zero, correct? Because of this. It is giving photovoltaic, but not long enough, recombination happens, it falls back to zero. This is the reason. The reason why we use salt water, cheap. Only to show to the primary school student that this device is workable. Photovoltaic is observed. We explain this part, the deflection to the right hand side part, but the deflection to the left hand side part, we don't explain to the school student. Just to show them photovoltaic is there. They got it. Are they excited?
Yeah.
Excited?
Yeah.
Number 6, electron injection efficiency in quantum dot MOS, meaning that the electron injection from the quantum dot to the TI2 has never been studied thoroughly before. So we are the pioneer for these 6 missing links, still looking for extra missing links to solve the problem in quantum dot solar cell, which the task of Kak Farha over here. She's working on that. So I think that I will explain all the 6 missing links tomorrow. Alright, that's all for today. Thank you. We discuss again tomorrow.